So in our introduction to series, so we're given a formal introduction to series, infinite series, numerical series, which means these are going to be series of numbers, and infinite series, which means we've got infinitely many terms. I like to start off by using the following motivation. We're going to study this number 0.9 repeating. Now, everyone, I'm sure, learned what it means to have a repeating decimal and was introduced to that concept before. What does it really mean? Well, one way to look at it is to say that it really means 0 with nines, ... Now, remember we talked about the ... means keep on doing it forever, right? And when you say keep on doing it forever, you can end up with maybe things aren't defined, right? Because remember, we had the example, if you have 1 times 1 times 1 times 1, or something that's very close to 1, and you multiply it by itself infinitely many times, sometimes the answer is E, right? Sometimes that limit is E. Sometimes the limit is 1. Sometimes the limit is plus infinity. So you have to be careful when you're doing an operation infinitely many times. That's why we have to have all of this structure around computing limits. So in terms of limits, 0.999 repeating really means the limit of this sequence right here. So the first term in this sequence would be 0.9, okay? Then 0.99. And each time we added another decimal place, we're getting closer to what we mean by 0.9 repeating, right? So we can label the terms of this new sequence here. The first term is S1. Okay, so you see we've got that there. S2, S3, S4, right? And so the idea is that 0.9 repeating is the limit as n goes to infinity of Sn. And now what is Sn? Because S4 is 0.1, 2, 3, 4, right? And so Sn would be 0. And you want to have nines. How many nines do you want to have? You want to have n nines, right? And so as you let n go to infinity, that's what we mean by 0.9 repeating. Okay. So here's the thing. So let's rewrite this again. What do we have here? So remember we had S1 is 0.9, S2 was 0.99, S3 was 0.999, S4 was 0.9999, right? And then we said Sn was 0.99 ... 9, and you have a total of n nines. Okay, S1, 0.9, isn't that the same thing as just 9 over 10? S2, that's 9 over 10 plus 9 over 100. Right? Another way to see that would be to say that's equal to 99 over 100, right? And then the 99 we can break up into 90 plus 9, right? So you get 9 over 10 plus 9 over 100. So S2, we can break S2 down. Okay, S3, we can break that down. And we can get a pattern. Now Sn, we can write as 9 over 10 plus 9 over 100, right? Now, why is this important? Because now watch this. Sn is the sum of, what's the pattern? 9 over 10, what do we want to say? 10 to the k. K starts at 1 and stops at n. So this is Sn. So we can use sigma notation to denote the nth term, right? Okay, so we said each Sn is a sum. So for instance, S4, for S4, we've got this over here. Each Sn is a sum, and we want to find the limit as n goes to infinity. This is what we want to find. The limit as n goes to infinity of Sn. So the limit as n goes to infinity of Sn really looks like that. And we said we could rewrite that as, so we'd have the limit as n goes to infinity of the sum k equals 1 to n, 9 over 10 to the k. Instead of writing all of this, we use shorthand notation and we just say from 1 to infinity, 9 over 10 to the k. Right? So that's where we're headed. That's why this is an infinite series. Now, notice that we've got terms. Right? So we've got terms. This time and what we're working with here, 9 over 10, 9 over 100, 9 over 10 to the n. That's what shows up right here. Okay? And we can rewrite this as a1 plus a2 plus an, ... and find a formula using pattern recognition, find a formula for the nth term, right, which is going to be 9 over 10 to the n. Okay? And so let's refresh and recap exactly what did we do. So we said if we want to create, or if we want to arrive at the number 0.9 repeating, here's what we do. First, we can start with this sequence of terms. What will our sequence be? 9 over 10, 9 over 100, 9 over 1,000, ... Next, we can create a new sequence. Our new sequence is going to be 0.9, 0.99, all the way up to 0.99999, where we've got n nines. Okay, and then finally, we can declare, or we can define, 0.9 repeating is the limit as n goes to infinity of our new sequence, right, of our Sn, which is the same thing as limit as n goes to infinity of that sum of 9 over 10 to the k, k equals 1 to the n. Because remember, that's what we're doing right here. So Sn, that nth term, is really adding up the first n terms up here, 9 over 10, 9 over 100, 9 over 1,000, keep doing it, right? Add those up and you get your new term. And then you want to take the limit as n goes to infinity of the sum of those original terms. Okay. So here's the bottom line. We can do this with any sequence, A sub n. So we studied sequences last time, and now we're saying that we can do this with any sequence A sub n. There's nothing special about A sub n, about using 9 over 10 to the n as A sub n. Nothing special about it. So here is our official procedure. You're given a sequence of terms. You're going to form a new sequence. This new sequence is called your sequence of partial sums. So we'll write this down. So this new sequence is your sequence of partial sums. Okay, and the nth term, the nth partial sum, is defined here. So this is your nth partial sum. All right. And then the limit as n goes to infinity of your nth partial sum is written like this. So one way to write it would be to say, I want to get in here and write this. Yeah, let me just go here. So if you have, so the limit as n goes to infinity of Sn, you write it as just the sum an n equals 1 to infinity. Okay. Now another way to write that, since Sn is really a1 plus a2 plus dot 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 plus an, so we're saying the limit as n goes to infinity of this is this infinite series. And sometimes you'll see it just written as a1 plus a2 plus a3 plus dot dot dot. Okay? So these notations all mean the same thing. Now, let's get into some definitions. Let me try to do a different color here. All right, so just go back. This notation here is called an infinite series. Okay, it's also just called a series. So when we say we're studying series, like we said in the beginning, I said this is our introduction to series, right? And we're studying numerical series, which means series of numbers, numerical, so everything is a number, and infinite series because our terms are going on forever. We're looking at that limit as n approaches infinity. Okay, so that's what we mean by a series. The numbers, A1, A2, A3, those are just called terms of the series. Okay, so you start off with the sequence. These numbers are the terms of your series. Now, they're also the terms of your original sequence, but that's one of the things we want to be careful with, is don't confuse the sequence with the series. So the terms of your series are A1 to AN, right? A1, A2, A3, and the numbers S1, S2, S3 are called the partial sums. So this new sequence, these are your partial sums. Okay, now, number 4, if your sequence of partial sums converges, then we say the series converges. So if your sequence of partial sums converges, then the series converges. If your sequence of partial sums diverges, then we say the series diverges. Okay? Why? Because your series is the limit of your partial sums. So if this converges, then the series converges, right? And if this limit, your partial sums diverge, then your series diverges. Okay, and the last thing we want to point out is that if the limit exists, i.e., right, if the limit of your sequence of partial sums exists, that's the same thing as saying if your sequence of partial sums is convergent. So all these different ways of explaining the same concept, right? So if that limit exists and is finite, if the sequence converges, same thing, then whatever your limit is the sum of the series. Okay? So for us, for example, we already know that we can write 0.9 repeating as the limit n goes to infinity of our sum here of 9 over 10 to the k. Let me say k equals 1 to n, which is the same thing as the sum 9 over 10 to the n equals, which is 1 to infinity. We want to know what is the sum of 0.9 repeating. That's the same thing as saying, let's compute this limit. Now, you probably were told that this is equal to 1. You were told, oh, that's the same thing as 1. Now we're at a place where we have the machinery to prove that 0.9 repeating is equal to 1, meaning we can compute this limit. Okay, so now we've got some warnings here. Do not confuse the terms of the series with the series. So for instance, when we're saying, what happened? Sorry, let me go back. So for instance, if we are saying, what is the limit of a sub n as n goes to infinity? That's not the same thing as what is the limit of the partial sums, n equals 1 to infinity, right? And it's going to come up, and you're going to do it, you're going to confuse the two concepts, but I'm going to remind you, don't confuse the two concepts, okay? When we have series, we'll have some questions. Here are the appropriate questions for us to consider. So this one here, these are appropriate. And appropriate means these are the questions that you're going to be expected to answer. So you're given a series, and the appropriate questions are: number 1, does the series converge? Number 2, does it diverge? If it converges, what does it converge to? What's the sum? What's the limit? And then the 4th is, can you make a good approximation for the sum? Now, we've got some tools. For 1 and 2, essentially, we'll be using convergence tests. And we've got all of these convergence tests. The key will be, when do you use which convergence test? That's going to be the issue. That's going to be what you're going to have to work on and practice, because you've got all these different tests. You've got to know when to use which test, right? Sometimes you'll use a test and it'll be inconclusive. You'll need to use another test. This is very similar to integration methods, where we've got 5 basic methods, and sometimes one method works and sometimes it doesn't, and you have to try a different method, you know. So the tests we have are the nth term divergence test. We have 2 comparison tests. Remember, I was telling you these are going to be actually similar and use the same ideas as the comparison theorem for improper integrals. Okay, so we have comparison tests, 2 comparison tests. We're going to have the geometric series test, the integral test, the ratio and the root test, and lastly, the alternating series test. So that's 1, 2, 3, 4, 5, 6, 7, 8. 8 different tests that we're going to learn about. These are going to help us to solve or answer the first 2 questions. Now, what about the third question? The third question, compute the sum, right? What is the limit? Very few of the series can actually be computed, right? You only need to know how to compute. So for this module, for what we're working on now, for the next exam, you only need to know how to compute for 2 types, geometric series and for telescoping series. So, for instance, if there's a question on the test that says, find the sum, you automatically know, either it's a geometric series or it's a telescoping series. Okay, later on in the following module, where we work on power series, then we'll do more. We'll be able to compute the sums for more types of series. But at this point, just starting out, we're just focusing on geometric series and telescoping series. Okay, and then so that was for the tools for the third, right? The third question, which is what's the sum? And the fourth question, which is, can you make a good approximation? So now this is going to be the most useful Okay, most useful. And it's very similar to the midpoint rule, Simpson's rule, trapezoidal rule, right? Where we've learned these techniques of integration by parts, U substitution, trig substitution, but then we also need to know how to approximate integrals when you don't have an elementary function that you're integrating. It's the same thing here for series. How do we approximate the sum of a series if it's not geometric or if it's not telescoping? Okay, and the tools for number 4. Do you remember how we're going to have a take-home exam? This take-home exam is going to be about answering question number 4, right? And essentially you'll have the integral test and the alternating series test to help you out with approximating sums. So 2 of these, the integral test and the alternating series test, not only do they tell you if a series converges or diverges, but they also give you an estimate for the limit. That's it. Thank you.